Hi, welcome to live tutorial sessions from JCBRO Labs. So in this video, today we are going to talk about 8051 programming in KEIL, and within this series we will be talking about machine cycles and how to provide delays using assembly language and how to do program in assembly language. And finally we will be toggling some LED, or we will toggling some pin of any port, and then we'll visualizing the same through logic analyzer, which is directly available within the KEIL. So there's a lot to learn, and I hope every one of you will stay with us till the end of this video. So let's wait for some time and let's other to join. Okay, so in the meantime, let's say, so if you have joined, you can type your name and the location from where you are seeing this video. So I asked this thing because it gives us the motivation to continue with this kind of free lessons, free and live lessons. Okay. Further, as you are aware, we will be asking some questions in between of this live session, and if you give the right answer, then you will win cash prize, right? So stay with us in order to win this cash prize. Okay. Okay, so let's continue with it. Okay, Ujjwal is saying he is waiting for questions. Okay, Ujjwal, we will be asking questions soon, and I hope you should give the right answer. Okay, so first of all, our today's first topic is the machine cycle. First of all, we will be talking about what exactly the machine cycles is and why they are used. So machine cycle, so every one of you know that 8051 is a digital device, and digital devices need some clock in order to operate. Okay, so in 8051 clock is provided with the help of a crystal oscillator. Okay, so if you have seen some of the hardware device of 8051, then you may have seen the crystal oscillators connected to it, and the frequency of the crystal oscillator ranges in megahertz. So generally 8051 is operated at 12 megahertz crystal oscillator frequency, or 11.0592 megahertz. I think it is 11.0592 megahertz. Yes. Okay. So for today's calculation, we will be considering this clock. So any crystal oscillator can be connected. So once this crystal oscillator connected, so inside this kind of clock frequency is applied to the internal circuitry. Now the hardware circuitry within the microcontroller, specifically to the microcontroller, is in a such that the frequency which is coming from this crystal oscillator is divided by 12 and then applied to the microcontroller. So if I say this is f clock, it will be divided by 12, and then this particular frequency will be used by 8051. Okay, so in other sense, if you are using this 12 megahertz clock, then ultimately 8051 internal clock to 8051 will be 1 megahertz. Okay, so now we will come to it, and let's denote this frequency fm as it will be f clock by 12. Okay, so it will be of 1 megahertz if we are using the external crystal oscillator of 12 megahertz, and it will be like this. Now this particular machine cycle is known as this is known as one cycle. Okay, so if this is 1 megahertz, so the time period of this clock is 1 microsecond. Okay. Now come to the main concept which we were talking about. That is the machine cycle. Okay. So machine cycle is nothing, just the number of clocks taken by the okay. So this clock or this frequency is also known as the machine cycle. So in our case, the machine cycle is of 1 microsecond duration. Now there's a each instruction take different number of machine cycles, right? For example, if I am writing move R0, R5, so this particular instruction is transmitting the content of this R5 into R0, and this particular instruction take one machine cycle. Okay. Similarly, there are some other instruction like DJ and Z. Okay, this particular instruction take 2 machine cycles, and return statements as well, so it takes 2 machine cycle as well. So what does we mean by that this particular instruction is taking this much of machine cycle? That means in order to execute this particular instruction, the time consumption by this instruction will be 1 microsecond. Okay, because it is taking one machine cycle, and the duration of this machine cycle is 1 microsecond. Similarly, this DJ and Z instruction will take 2 microseconds. So think about, if we have written a longer program of thousands of instructions, then you can calculate how much time consumption will be or how much time that particular program will take. Okay, so that is why this is very important, because when we talk about some of the embedded system in critical applications, so we have to be very careful about the instructions which we are going to use there. Because and we should know the time taken by these instructions in advance, so that we can optimize our program accordingly. Okay, so this was about machine cycles. Now the next thing comes, which we are going to talk about is the delays, or sometimes also known as the loops. We will be talking about loops within this assembly language, or calling subroutines, and also. Okay, so there are several instructions which are used in assembly language, and particular in 8051. Some are known as the jump instructions. Okay, so what are the jump instructions? Let's say you have written certain instructions, and then here is a jump instruction command, and then there are other instructions, right like this, right? So through this jump instruction, the control can jump to any other location. So you can think of it as like a go to statements. Okay, now within this go to statement, we don't have any return command. Okay, apart from that, there is some call instructions are also there. All right, call instruction. So within jump instruction, like there are different jump instruction like DJ and Z. So DJ and Z is like, if we write like 3 and the, let's say I am writing here, so this here is known as the label at which location it will jump, and this is the content. So it will decrease the content of this R3 and will jump to here if the content of R3 is non-zero. Okay, as soon as this content of R3 will become 0, it will not jump and it will go out of it. Similarly, there are other instruction to jump like JZ, so it jumps when content of accumulator is 0. And similarly, there is other instruction like J and C, so it is jump if there is no carry, that means carry is 0. So you can go through these instructions from the manual of 8051. Now similarly there are other jump instruction like LJMP. Okay, so it is long jump. So long jump means it can jump to any location within the program. So our program is of remember 8 kilobyte. We have total 16 bit of address, right? So it can jump within any location of to any location of the program within that 16 bit addresses. That comes out to be 64 kilobyte of memory. Similarly, there is another instruction that is known as SJMP, and it is the short jump. So short jump have a specific location. It can jump to 1-8 to 128 addresses from its location. Okay, so it can jump either 1-8 to above side or plus 1 or plus 128 bytes to the lower sides. Okay, there is only generally there is a problem. It is minus 128 to 127. There is one location because 0 will take something, right? Similarly, there are call instructions. So call instructions are used to call subroutine. So these subroutines you can think of like the function in C language. So how this call instructions work? So let's say these are the addresses, right? Address will go here, and you have instructions here. Okay. Similarly, you have some separate subroutine which is written at some other location. Its address is something else, right? And it is written there. And at the last, a return statement will be there. And here is a call instruction, right? And then again the program. So as soon as it is very necessary to understand the functioning of this call instructions and the effect of this call instruction to the other registers of the program. So as we said, the program counter will be denoting this call instruction, and when this call instruction will be executing, program counter will be having the address of this next instruction to be executed. But as soon as this call instruction executes, now because this call instruction we are trying to transfer the control from here to this subroutine. We are going to this subroutine. So in order to go that subroutine, the program counter content has to be changed. And when this return statement is there, so the whatever the previous content of program counter was there, that has to be extracted as well, right? So what happens as soon as this program call instruction executes, the current content of this program counter is shifted to the stack. Remember, we talked about stack pointer in our second lecture. So that goes into the stack, and the next address at which it has to jump, that keep loaded into the program counter. Now program counter starts denoting this address, and then it executes, and finally when this return statement is executed, the data is popped from the stack and that is loaded into the program counter. Now program counter start denoting the next instruction to be executed. So I hope you got it. As soon as this call is executed, the present content of program counter goes to the stack, and the next address where this program counter will jump, that particular address is loaded into the program counter. Then program counter keeps increasing, and CPU start executing those programs, and in return command, the program counter, the previous stored data, the address of the program counter popped up and stored into the program counter, and then program counter starts executing the normal routine. Now you can easily think of now what is the conflict between stack pointer. Now some if let's say stack pointer denotes the 07 in the RAM, right? So it will become 08 after putting some address into it. Now 08 is the register 0 of register bank 1. So if in this entire program you are modifying the content of this R0, then your program will go hosh posh. So I am saying hosh posh, that means it will stop working, because if you have modified the data of R0 and you have not changed the content of R7, So when this return command is executed, the uh, wrong address will be fed into the program counter, and program counter will go somewhere and your program will behave like a haywire. Okay, so you will not be able to execute the current execution of your program. So that is the very important work of stack. And so generally what we do, as soon as if we are using call instructions, or we know that we are going to modify the register content, as soon as we start the address, we transfer some of them some other location of RAM into the stack pointer, so that when we return it comes back to it, so we don't get lost in between. Okay. So now there are several instructions for this call routine. Those are lcall. So lcall is long call. So the address of this subroutine can be anywhere within the 64 kilobyte of memory. And then there is another one, a call. That is the absolute call. So this a call is a 2-byte instruction. So we can go up to this. That means uh, within this 2k byte. Okay. So within this alcohol we can go anywhere between 64 KB of memory, right? Any addresses. With this A call we can go up to only 2 kilobytes. So that means from its present location to within the 2 kilobyte of addresses we can jump at a time. So these two instructions are generally used. Okay. Now if we talk about the machine cycle consumed by these instructions, so this DJNZ takes around 2 machine cycle. This jump instruction, most of these jump instructions take these 2 machine cycles, right? So if you go through the instructions of this 8051 through manual, you will find a number of machine cycle consumed by different instructions. So let me just verify. Yes, a call take two machine cycle, L call 2 machine cycles. So most of these jump instructions take 2 machine cycles, including this DJ and Z. Okay, so I hope this is clear to you. Now coming to our next concept, and prior to the next concept, okay, Sally Tyagi has good afternoon, Sally. And so, okay, prior to going to the next topic, we are going to talk about our first question, and that is how many addressing modes are supported by assembly programming of 8051 microcontroller. Okay, so I am repeating the question. How many addressing modes are supported by 8051 microcontroller? So whoever will give the first answer will get a cash prize. Okay, so just think about it or search about it, and in the meantime I will introduce to my new topic, and that is very important, is the delay calculation in assembly. Okay, so some of you might be thinking, why this delay calculation? So sometimes we intentionally require some amount of delay between the instructions. So let's say these are the 2 instructions, and we want to execute these 2 instructions at certain amount of delay, let's say at an interval of 1 second or at an interval of 10 milliseconds, and so on. You will learn in between, like how why these instructions. Okay, Ujjwal Sharma has given the right answer. So okay, sorry Sally Tyagi, Ujjwal Sharma was the first one to give the right answer. So Ujjwal will win. So this prize goes to Ujjwal for 20 INR, and I hope Ujjwal will share the screenshot of this prize to our social media sites, so that other people can also get the benefit of it. Okay, so yeah, we were talking about delay, right? So it could be anything. Now we know, now the question comes, how can we provide the delay? So there are two ways to provide the delay, through instructions or through timers. So till now we have not learned about the timers. So in this case, or in this particular lesson, we will be dealing with how to provide delay with the help of the instructions. Okay, so you have learned like all the instructions take certain amount of machine cycles. For example, DJ and Z take 2 machine cycle, and machine cycle, if we are using 12 megahertz of crystal oscillator, then machine cycle time was 2 microseconds. So this DJ and Z will consume 2 microseconds if it is running at one time, right? Now if we run this DJ and Z continuously for 100 times, so it will give us 200 microsecond amount of delay. So that is the very basic concept to provide the delay in between. So I will give you the entire process for it. Okay, let's learn it with the help of some example. So let's say you want a delay of 1 millisecond. Okay, we want a delay of 1 millisecond in between two instructions. Okay, so what we will do, from this 1 millisecond we will take number of machine cycles required. So one machine cycle is taking 1 microsecond amount of time. We need total 1 millisecond. So total number of machine cycles required will be divided by 1 into 10 to the power minus 6. So it will come out to be 10 to the power 3. That means number of machine cycle we need is 1000. Okay. Now we will be using this particular instruction, like we will put some content into here R3, and then we will be keep on jumping here only. Okay, so it will be keep on jumping, so it will jump on here for the amount of till this R3 is not 0. Okay, now we need total 1000, and maximum value which we can pass into R3 is 255 times. Okay, why 255 times? Because this R3 is of 8-bit. So maximum number will be 255. So this particular instruction, single instruction, we can run 255 times only. So number of machine cycle consumed by this will be, so this particular instruction will consume 255 into 2. Okay, so it comes out to be 0 on 510 microsecond. Okay, so if we run this entire instruction 2 times, then our work is done. Okay, so we can require number of registers you can think of, because one register can hold 8 bits. So number of register is number of machine cycles divided by 255 times. Okay, or you can think of one will give this answer, then how many times you have to run this particular instruction 255 times. So let's do calculations, open calc. So if we divide 1000 divided by 255, it comes out to be 3.9 or near about 4. So that is wrong, because we have to do it by 2, so near about 2. So approximately it will come out to be 2. So how we will write it, right? So this is the instruction. Here we will call a call, we will pass a delay here, right, like this, and then delay will be called, right, and within the delay we will pass move, let's say R2, so it could be anything, right? So R2 it could be like we can pass hash 0 to h, and then we'll pass move R1 comma hash 255. Okay, and then we will keep on jumping here. So right? So we'll type dj and z r1 comma here. Okay, after delay normal execution, and then we will jump on here, and then we will jump again one times. Okay, it should be 0 1 only. So we will be typing dj and z r2 comma uh, here 1, and then return. So let's think about it, and let's learn about how it is happening, right? So as soon as we jump to here, r2 content will become 0 1h. Okay, decrement and jump. Okay, I think it should be 0 2 because it will jump here. So r2 will become 0 2. Then from this command, r1 content will be 255, and here it will jump if rn here. So it will keep on running this execution till 255 times. So because it will decrement the content of r and jump if it is not equals to 0. So this instruction will execute 255 times. Then it will come here, it will decrease the content of r2. So r2 is 0 2, and it will decrease one more time, right? And then it will decrease the content of r2. So r2 content will become 0 1, and then it will jump to here 1 again. So here 1, this will go here. So here 1, we are again reinitializing the value of 255 to r1. So the execution will come here again. So it will again start decrement jump. So again it will run for 255 times, and then it will come here, and then r2 content will be like 0, right? So decrement jump if not 0, and then it will come out of it. So if we talk about how much delay which we are getting, so you can think of this particular delay, entire delay subroutine. It is taking one machine cycle, it is taking two machine cycles, and it is running two times, right? So this particular instruction will take 255 into 2 times of machine cycles, and it will take again 2 machine cycles. So if we compute the delay, so basically this is the major portion. So we can think of 255 into how many times it is running, multiply by 2, and then again, because we are running it 2 times, then 2 times, and then plus you can add additional machine cycles, plus it will run once, 2, and this return will take 2 machine cycle. So this many of machine cycles will be taken by it, and overall time duration you can then compute. It will be windows plus, let's multiply it, 255 into 4 plus 2 4 5 plus 6. So it comes out to be around 1026, and this much of machine cycles, right? So one machine cycle duration was 1 microsecond, so it will take 1026 microsecond or 1.026 millisecond. So it is nearly equals to what exactly we were trying to do. We were trying to compute 1 millisecond, so it is very near to that. Okay, so this is the overburden we have to take care. So so by through this coding, you can think of like, okay, by this entire thing you can exactly compute how much time your entire program will take. Okay, now we will be coming to today we are going to write program on this delay subroutine and how to provide this delay. Okay, let's go to new. Okay, our new question is, prior to going further, let me ask you another question, and then you will also get a chance to win the prize. So our next question is like, okay, let me see what was the question. Yeah, how many ports do 8051 have? So how many ports are there in 8051 microcontroller? So that is very basic and very easy questions. Easy question. I hope you will give the answer soon enough. Okay. So in the meantime, let me introduce to the program which I am going to talk about, or which I am going to write. So the question is, how many ports are there in 8051 microcontroller? Okay, Mr. Jitendra Kumar has given the right answer. That was fast. So he has won 30 rupees INR cash prize for today. Okay, so we will share a link with them, and this Jitendra and Ujjwal Sharma, you can send us a mail with your mail, and then you can send us a mail at info@gcprolabs.org, and then we will send you the link for filling up the form so that you can put your details, and then we will transfer the amount. So our program is like this. There's a microcontroller, and on this microcontroller of pin number, let's say 1.2, so it is port 1 pin 2. At this, we want to generate a clock frequency of, let's say, 1 kilohertz. Okay, so when I am saying we are going to talk about to generate this 1 kilohertz frequency, so the program would be simple, like set bit there is a instruction like set bit set b, or then clear, or apart from that we can also do a simple calculation, like we will be passing move p1 as hashtag, because let's talk about this. This is the p1 register, 0 1 2 3 4 5 and 6, and then 7. So we want to do 1 or 0 at here, at this location, right? And all other location will send 0. So the corresponding hex code will be 0x04. So we'll be transferring 0x04h, and then we will be calling a call delay, and then we'll be calling again move, right? Like we'll be calling move p1 comma hash 04h. Okay, yes, simple. And then we'll be calling a call delay, and then we will, because we want to do it again and again, so we will be writing like sjmp here. Okay, so it will jump here. Okay, so this will be where we again our delay program will be written somewhere. Now within this delay program, the question is how much amount of delay do we have to give. So because we want to generate a 1 kilohertz frequency, so this entire duration is 1 kilohertz. That means we want to go only for half of it, for this much amount of it. So if this is 1 millisecond, so time period is 1 by 1 millisecond, and half of the time period, because for half time it is on, for half time it is off, so entire period is 1 kilohertz. That means time is 1 millisecond, half is 500 millisecond. So what should be the content of 500 millisecond? Not 500, not 500, sorry, it is 500 microseconds, right? So how many machine cycles do we need? We need, so let's talk about, so required machine cycles for 500 microseconds is, it is simple, 500 machine cycles. If one machine cycle is taking 1 microsecond, so we are assuming a 12 megahertz crystal oscillator. Okay, so we'll need 500 machine cycles, and we will be using DJNZ, right? So within DJNZ we can put R2 content as 250, because that will take 2 machine cycle and we will run it for 250 times. We'll all over this, right? So that will be easy. So let's say we will be writing here move R2 comma hash 250, and then here it will be DJNZ R2 comma here and then return. So this entire subroutine will give us a of 500 microsecond delay. And let's check it, let's verify it whether we are right or not, and we will see this particular waveform with the help of logic analyzer. Okay, so now coming to the our programming part. Okay, before programming part, let's talk about our question. So this is the next question. Okay, that is a little programming, so have a closer look on it. So if move r0 is 05h, and then we are writing this command 25h comma r0, and then we are moving a comma 25h, then we are adding a comma 25h and then add. So I hope now you know. So my question is, what will be the content of A after execution of this entire program? Okay, so again let me repeat it. What will be the content of accumulator after execution of this program? Okay, so with that, let's jump to our work. So we are creating a new project. So okay, so we will create a new project into the same library, into the Dropbox, and we'll go to live 8051. Okay, so we will create a new folder, third delay program. Okay, I think, okay, that's good, Sally Tyagi, you have given the right answer. So again, for you we have this higher price of 50 INR because it was a little programming part. Okay, Ujjwal, you were late this time. Okay, so this 50 INR will go to Sally Tyagi, and we'll share the link with him or her. Right, now coming to here, we are creating a program, delay program, and in this delay let's call frequency generator. Okay, we'll select a microcontroller AT89C51. okay, yes. So now in this tutorial series we are moving towards the more programming part, and soon we will be start using Proteus, and we will be also demonstrating this program with the help of with the help of hardware as well. Okay, so let's create the assembly file. So we'll go to add new item, and we'll create ASM source file, and then we'll write the same source file as main program, and then add. So here comes our main program. So first of all we'll type org00h, so it indicates like we are starting from 00 memory location number. And then remember, because we have to repeat it again and again, so we are transferring move p1 comma hash, so So if you remember our data, so this was the data. We have to pass 04H in order to toggle this pin number 1.2. So we'll pass hash 04H and then we will call a call delay, and then we'll pass again. Okay, so we want to put everything in the same. Equal to move p1 comma hash 00h and then a call delay and then sjmp again. Now we'll go to delay. We'll provide delay this one. Okay, and within this delay, let's write it here. First of all, we'll provide move r2 comma hash 200. So it is not hexadecimal value, it is normal decimal value, and then here we'll writing dj and z r2 comma here, and then we have to type ret command, and then at the end we'll type and. Okay, so this looks fine. Let's see, move p1 and so on. So let's first compile it. Okay, so we are rebuilding it. Let's see if there are any error or not. Okay, okay, there is no error, right? Now we'll go into the debugging mode. Okay, here. So within this debugging mode, we will go to view. Okay, let change the scene. Okay, we'll go to the view and we'll go here, and there is some watch windows. Now analysis window, logic analyzer. Okay, so here is our logic analyzer. Yeah, so I hope you know logic analyzer. It presents the status of any pin can be plotted here. Okay, and we'll also, okay, that won't be visible. Now in this we will go to setup and we will add here p 1.2. okay, p generally there is a format p 1.2. okay, let's say p1, and its value can go from 00 to 255 decimal value, so it will be 4 and 0, right? Because this we are seeing the entire plot. Okay, so maximum value we can change it to go to 04 and then 00. Okay, and then close it and let's run it. Okay, you're seeing this nice waveform, it is coming up, which is generating. So it is showing you the complete content of port 1. So if we look at the content of the port 1, so port 1 content is this one, that is 04H, right? And that is why you are seeing this kind of waveform here, and this axis is 0 to 4, right? Now let's stop it, stop the execution, and let's do some calculation whether we are getting the right amount of delay or not. So what we'll do, we'll zoom in. Okay, now if you go here at the first location and click, it will start the marker there, and then if you go to the second point, it will give you the time duration. So if it took about delta, So delta is around 0.2045 millisecond. Okay, I think we did some mistakes here, and if you go here, it is 0.5 milliseconds. So our frequency a little bit high. Okay, let's stop over here. What could be the reason for that? Okay, there is option here. Go to options for target one, and here in the target you have seen the frequency has been selected to 24 megahertz. So let's change it to 12, and then okay, and then save it. So it was the simulation, so whatever frequency we select, it decides accordingly. Now let's go to the debugging mode again, and let's run it again, and then stop it here. Now this looks double to the previous one. Let's see. Okay, here is first one, and if we look at the delay, okay, it is around 407 milliseconds. That looks fine, but still that is, it is not 500 millisecond. Okay, okay, we have, oh, sorry, it should not be 200, it should be 250. I think I computed 250, yeah, but during the programming I forgot it. Okay, so it is 250. Let's compile it again. Okay, let's go to the debugging mode, let's run it again. Okay, and then stop. Okay, now if we see here and we go here, then you will see, yes, it is 0.508 millisecond. That is nearly very accurate. And then if we talk about the frequency of this clock, so it is from high, from this to this, so it will be, delay is around 1.016 millisecond, and frequency is 984 hertz. So it is very near to it. So from here you can understand, okay, extra amount of delay will be taken by these commands. So instead of making it 200 exactly 250, we should compute for the lesser amount. So let's say if we make it 248, so this thing you can do in order to make it proper, or in order to compensate the other delays, and compile it and then debug it again. Okay, so let's run it. There is, so now if we see is how much amount of delay we are getting. So now that is, it has reduced to 0.504 millisecond, and now it is 994 hertz, right? So it is more accurate. Okay, so from here you can compute the exact amount of delay, and based on exact amount of machine cycle which are being consumed. Okay, so from here you can compute exact amount of machine cycle which are being consumed by this code, and based on that you can modify this number. So it will be a very less modification, but through this calculation which I just told you about, delay calculations, from this calculation you can get the values, the major values, and the final modification that can be done afterwards. Okay, so I hope we have covered all of our today's topic, and then we will stop here, and then we will continue with the programming in C in next class. Okay, so from in next class we'll be talking about how to program in C language. Okay, so there is Salesh Raja circuit design की भी start circuit design classes. Okay, so what kind of circuit design? Okay, we will be using a protest from the next class, because from next class onwards we will be using programming in C language, and then we will be using protest to simulate the program as well. And during that programming part, we will be demonstrating the entire thing uh, with the help of protest. And so in protest we will be creating the entire circuitry. So classes will be start getting more interesting in upcoming videos, and we will be interfacing a lot of real hardware with 8051 microcontroller. So that is for today. I hope you will join us live again on the next session. And the next session for this 8051 microcontroller will be on 29th of June. Right. In the meantime, you can join our other online sessions on Python and Matlab. So that's it for this video. Finally, we also provide online training, helping technical assignments. We also do freelance projects based on data science, Python, machine learning, etc. So if anyone of you any requirement, then you can contact us through our website, which is www.jcbrolabs.org, or you can also mail us at info@jcbrolabs.org. So that's it for this video. Thank you.